Hello everybody. For discussion number 13, I will be doing a problem from the textbook. It is section 15.4, number 19, and it asks us to use Green's theorem to evaluate the line integral of x minus 3y dx plus x plus y dy with the boundary of the region lying between the graphs x squared plus y squared equals 1 and x squared plus y squared equals 9. So before I did anything, the first thing I did was graph these two boundaries, x squared plus y squared equals 1, and x squared plus y squared equals 9. I know that both of them are circles, and I know that the first boundary has a radius of 1, and the second boundary has a radius of 3. So here we are going to graph what that will look like. So the first one, as I said before, has a radius of 1. So that is the circle. And the second one has a radius of 3. And when they're talking about the boundary between the regions, they are talking about all of this. Okay? So this graph is going to help me decide what my boundary for the integrals are going to be. Well, I do know that my r, I'm going to put this right here, is going to be, has to be from here. So I would make my r 1 to 3. So I'm going to put that right here, 1 to 3. And my theta is going to be from 0 to 2 pi because it's going to make a complete circle. So if I'm starting here, it's going to be 0, and it's going to go all the way around to 2 pi. So I'm going to put that in here, from 2 to 2 pi. Okay, there's pi. And everyone knows that the Green's theorem is this equation right here, which is the double integral of c of m dx plus n dy equals the double integral of the region of dn over dx minus dm over dy of dA. So what we're going to do first is going to find what dn over dx is and what dm over dy is. So this is our m, this is the equation we're doing. This is our m, x minus 3y, and this is our n, x plus y. Okay, so we're first going to do what dn dx is, and that is going to equal to, so we're taking the derivative of x plus y right here, and that is just going to be 1. Okay, now we're going to take the dm dy, and I'm just going to put, okay, and that is going to equal, so we're taking dm of dy of x minus 3y. Well, everyone knows that we can't take a derivative of y, there's no y in the x, so it's just going to be this one, negative 3y, is just going to be negative 3. Okay. Now we could put these into our equation. Okay. So I'm just going to make the equation for us. So, okay, we are taking the integral, and we're going to do a double integral. Okay. So we're going to do the theta on the outside and then r on the inside. So it's going to be 2 pi from 0 to 2 pi. And this is going to be from 1, oh, that should be a 3, I'm sorry, to 3. And we're going to do dn minus dm dy. Wait, dn of dx minus dm dy. So that's going to be 1. So what is 1 minus negative 3 equals 4. So we're going to put 4 in here of r dr d theta. Okay. So this is what we are going to be evaluating. Okay. So I did this a little before because it takes up time. So the first thing we are going to do is we're going to put our 2 pi in here. Going to make this a little bit bigger. Okay, 2 pi, so we're going from 0 to 2 pi, and we're taking the integral of 4r dr, so that is going to be 4r squared over 2, which you're going to cross out the 4 and the 2 to make it simpler, so it's going to be 2r squared from 1 to 3 of d theta. Okay. Now, we are going to evaluate this even further. So we have from 0 to 2 pi, so 0 to 2 pi of 2r, okay, so we're going to do 3 squared minus 1 squared d theta. And we're going to plug in all the numbers. So 3 squared is 9 minus 1 squared. So 9 minus 1 is going to be 8. So we are going to ultimately have the equation to be from 0 to 2 pi of 2 times 8, which is 16. Okay, now we are going to take the integral of that. Oh, that should be a 2. And we are going to get 16 theta from 0. Oh, I don't know why that's happening. From 0 to 2 pi. Oh, yes, and that's just there. Okay, from 0 to 2 pi. So we're going to plug it in. So 16 times 2 pi minus 0 is going to equal to 32 pi. And that is our what we evaluated. Okay, I hope this helps, and everyone good luck on finals. Thank you.